Is this your first time in MRI center? For all of you?
I've done cognitive neuroscience,
Mm-hmm.
so I came here.
You attended my lecture before? No, right? You came here to the staff? Or?
For cognitive neuroscience.
For the class. With Karthik. Okay, so Karthik was presenting.
Yeah.
Okay, good. So, I'm not using the same slides. Okay. Why do you think these two hemispheres are different?
So they are different? In what way they are different? Okay.
Sorry?
One has like more ridges.
Yeah.
It looks more solar than
Sorry?
Neurodegenerative.
The whole half my hemisphere is neurodegenerative. This is actually my
Oh,
brain.
this is your brain.
It's my brain. I should be like, like It explains a lot, yeah. And there's no cerebellum in that. If you look at the bottom, there is a cerebellum in the brain. Where's one of this model? So the model in your hand is missing the cerebellum, it's missing the
Is it
subcortex.
really missing?
Well, it's digitally missing. It's physically, you don't see it. But yeah, we did digital changes.
Okay. It's possible to remove digitally any part of the brain.
You're looking at. So what I removed in this side, you know, we'll talk about it. You guys are engineers, physicists. What are you?
Mixed.
Chemist. And what kind of engineering? Bioengineering. Okay. I'm a bioengineer, so welcome to the club. So, so what's on top usually is the cortical layer, the cell bodies. So this is where your functional centers. Like, you know, think about the Ministry of Defense and the Ministry of Education. But the way they communicate with each other is through roads, you know. Think about Shetlai roads, think about Al Ain road, okay? So then the roads are the white matter structure. They sit under the cortical layer. Yeah? Do we have the color? Yeah. So, okay, well, we should start.
Let's start,
We should
yeah.
start. Yeah, we should start. We'll talk about this. So on the top is the cortical layer. So, for example, this blue thing is the motor cortex. Yeah? And then underneath it, the cable that takes the instructions from the motor cortex to my hands is actually carried through the axons, the white matter. So that's why it's just digitally removing the cortical layer so you can expose the highways underneath it. Okay, so at least that's my hope. I'm not. I don't have significant brain atrophy. But okay, so now I introduce myself. I'm the MRI physicist. I'm Osama. This is my colleague and my boss, Haiti. She's the MR technologist. She's the boss of this place. If she orders us to leave, we should leave, including me. Okay. So, I mean, you kind of know what MRI does, but if in case you missed the memo, you've been living on the rock for the rest, for the past few years in your life, like I was in 2005. I have no idea what MRI does. In a nutshell, MRI takes pictures. It's just a camera. The only difference about this camera, it takes pictures of the inside of your body. Yes. To look at the structure, look for foreign objects. And it's also used to assess the function. Okay? What you like, what you don't like, can you move your arms, which areas are specialized for what function. We have visual cortex, motor cortex, sensory cortex, language cortices, and you name it, yeah? And a lot of times we also look, I think is the most important part, is we need to look at the structural functional relationship to see if this can play. Okay? So every organ has a structure and has a function. And there is a disease or whatever insult affecting the structure, the function will suffer, and vice versa. Yeah? So the brain has a function to, say for sensory, vision, language, and a lot of very important functions. But also you can, whatever we're going to discuss today about the brain, it also extends to the heart. It has a structure, double helical, fiber pattern, blah, 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 that can actually make it pump efficiently. The kidneys have a structure that actually can filtrate the blood. The liver, similarly. So all the organs in the body have a structure and a function, and MRI is just a camera or a tool that allows us to study the structure and the function together, and maybe start making some inference about the structural functional relationship. Okay, so it's just a tool with a purpose. Okay, all right. So, yeah, you're taking an NMR course now, right? This is an NMR course. Oh, wow! The first class I should not talk about the NMR phenomena, but I'm not going to talk about it because I'm not qualified enough to talk about the NMR phenomena. I just have a cartoon about the NMR phenomena. Okay, so this is what we tell the students that haven't heard in their life what NMR is. It's some nuclei, not all of them. We can talk about hydrogen, carbon 13, not carbon 12, right? Phosphorus 17, sodium, yeah. Some nuclei have nuclear magnetic moments. If you put them in a magnetic field, I'm representing the field with blue arrows, equal length, okay, they will pick up an angular momentum. And through, I think maybe you derived Zeeman splitting and all that, okay, with some quantum equations that makes no sense to me, you end up with a spin. You end up with a magnetization vector. Everything before this is quantum mechanics, quantum mechanical phenomena. But we can describe this magnetization vector, with classical physics. That means I have a magnetization in the Z. I can tip it by 90 degrees, then my Z component goes to 0, and my X component goes to M0, right? If I start with M0. There is relaxation, T1 and T2, we talked about that. Awesome. He knows more about T1 and T2 than me, so I'm gonna, know my level of knowledge here. Okay, so this magnetization, the three words, magnetic resonance imaging, right? The magnetic part is we polarize the spins by putting them in a strong magnetic field. The stronger, the better, right? The stronger the stronger the field, the bigger that red arrow, right? The bigger my M0 signal. It's field dependent. And inside this arrow, you have like billions and trillions of these spins precessing at a Larmor frequency. That frequency is depending on two factors. The nucleus at question, for example, for hydrogen, is 42.56 megahertz per Tesla, and the field strength, right? So and then that decides how fast they go. To be able to speak to them, to talk to them, to perturb them out of the equilibrium, you can apply radio frequency pulses, okay? And if you apply it on resonance, okay, we always say the swing analogy. If you want to maximize your swing height, if you do small pushes at the right frequency of that swing, you will actually maximize your energy transfer, right? Similarly, the magnetization is going to take your energy if you apply on resonance, and then it doesn't like it. It wants to come back to equilibrium. It's experiencing a V0, and you talked about block equation, gamma M0 cross V. So it's a cross product. As long as the magnetization is perpendicular to the magnetic field, it will do angular momentum. It's going to come back. As it's coming back, it's relaxing, right? And it's a little magnet precessing in an antenna, and that generates through nuclear induction a voltage. That voltage has an oscillation frequency, and it decays when magnetization comes back to equilibrium, right? Okay, how do we study this? I'm sorry, but I didn't realize that you guys, know Fourier transform. All of you? Awesome. So if I tell you, okay, here's a quiz. Define Fourier transform. Yeah.
You take a wave that's a superposition of several waves, and then you
divide them into their components.
Bravo. Yeah. So you avoided the common trick. It's like, oh, it's the integration from minus infinity to infinity. No, you don't say that, right? You know, I have a different way to explain Fourier transform. It's a mathematical prism that breaks my input signal into its fundamental frequencies. The same way a prism breaks a light into its fundamental frequency. Why? You know what the delta function is? No, okay. White light has all the visible light frequencies. A delta function has all the frequencies. Okay? So white light is your delta function. What happens if I shine red light here? I'm gonna come out with red light. Okay? Because it's a fundamental frequency. Same way, I analyze the signal with a mathematical prism. We call it Fourier transform. If I Fourier transform that, I get a peak, right? And that's the free water peak. NMR guys don't like that peak. They usually suppress it, right?
Water,
Yeah, you suppress it because they're interested in the little peaks that don't resonate at the same frequency of the free water because they want to look at hydrogen, blah, blah, blah. I don't understand what he's doing, okay? But what I know is this is pretty boring, okay? It's like, all right, other than the chemistry part. But if you say, I put my water bottle inside the magnet, I give it energy, it relaxed, and I generate it, and I get this, so who cares? Okay? Other than that, chemistry people. Until somebody came in the 1970s, like, oh, if you put a tumor tissue in an NMR machine, then you have different relaxation, different FID than the normal tissue. And that actually spun the interest of drug companies at the time in the 1970s. It's like, oh, maybe we can use NMR. Has been used in the 50s, 60s to study chemical structures for like medical applications. And what did we do to this sample? Nothing. We just put it in a magnet, gave it an RF frequency, and we record the signal. The RF frequency we're talking about is in the 120 megahertz at this thing. They have 500 megahertz, or your cell phone is running at the gigahertz. So it's not high frequency, it's non-ionizing radiation. I'm not using X-rays. It doesn't cause cancer. I'm not using radioactivity. Yeah, I'm not using gamma wave, alpha waves, whatever. I'm using just radio frequency. It's very non-invasive. And I didn't have to do anything. It's the endogenous spin, atoms in the tissue. In our case, humans, we are made of lots of hydrogen because of the water. So it's very convenient. It's low sensitivity, but I have a lot of it, so might as well I can get a signal. And this is what you're looking at here. Fast forward of actually this slide is coming. This slide is actually not this. Slide is the next slide. You studied K-space? You haven't studied K-space? This is not the slides for this lecture. Okay. Good. Yeah. Sorry. Okay. The problem with this is if I put the head here, this is actually our colleague, she's a postdoc in NYU. If I put her head in an NMR machine, 500, it doesn't fit, let's say it fits. And I do an NMR experiment, I will get a single FID and a spectrum from the whole head. What's missing with NMR? Yet, spatial localization. Okay, so now, did you study gradients yet? Okay, good. So that's what upgrades an NMR spectrometer, that's what you have in ERB, an imaging machine, okay? And we can upgrade, we can add an imaging module to those NMRs to make them imaging. But an NMR by itself cannot spatially localize where the signal is coming from. Ideally, you want to have a sample that's very homogeneous, and you get one signal from the whole sample. Okay? It doesn't work for a brain with a tumor on the left side, in the sensory cortex, to be specific. Right? So what we do, we have some spatial localization. How do we do spatial localization? We add a new magnetic field. So far we have the B0, the strong magnetic field, the radio frequency, the B1, and now we added a G, gradient. Okay? And the G, the gradient, affects the alarmar frequency in a known pattern. So let's say I have an X gradient and the x-axis. I just taper my magnetic field slightly in the order of milliteslas. Okay? I have a 7 Tesla, I say 10 millitesla per centimeter. 80 millitesla per centimeter, whatever, yeah? It's just a small millis of Teslas, just I need to taper it. What happens when I taper it? Then my system doesn't have the same normal frequency anymore. The normal frequency it's gonna be spatial dependent. It's gonna have a spatial component to it. We can do this in the Y, we can do this in the Z. Okay? So then, that's all what we do. We just add a gradient, we apply the pulse, we record the signal, and that's what we get an FID. Okay, well, this is similar to an orchestra, by the way. If you close your eyes and the cello is one side, the drum on another side, okay, your ear is gonna receive one signal, but your cochlea is doing Fourier transform. It's breaking the frequencies. So you can perceive, it's like, okay, I know that the cello is on the left. Then your ear is recognizing that there is a cello playing and the drum is silent. And then when the drum is playing, it's the same signal, it's one signal, but your cochlea, it looks like a snail. It's actually doing a Fourier transform on the fly for you. Yeah? So it's very similar to an orchestra. I make the spins sing at different frequencies depending on their spatial location. That's all that we're doing with adding a gradient. That's half Nobel Prize 2003. Okay, here's a signal. How do we analyze it? Mathematical prism, Fourier transform. What do we get? A projection. Okay? This projection, you can think about it as if I integrated the spatial information perpendicular to the x. It's a projection. Okay? Lauterburg came in the 1970s. He modified an NMR spectrometer at night because chemists had to use it in the morning. He added gradients. He wired it himself. He was able to do like only 4 gradients: x, y, xy, and z. Just like 4 gradients. He used CT technology. Are you familiar with CT? Familiar with X-ray? Light, shadow, but the light is X-ray. Then if you rotate, you do light, shadow, and you collect projections. Okay? So you get a 3D volume, you break it into multiple 2D projections, multiple shadows, and with ancient math, invented in the 1500s, somebody came with a computer, did something called filtered back projection, and that's where we get a 3D CT image. So Lauterburg used back projection, that's used in CT, to convert these 4 projections into an image. This is hard water, this is regular water. Deuterium, is that what it is? Yeah. Hard water, heavy water, and this is also not hard, heavy water, yeah? Heavy water and regular water. It's like he sent it to nature, reject. He rebutted, it's in Wikipedia, I'm not gonna tell the story, it's published. And you're looking at the paper that gave him half the Nobel Prize in 2003. You're looking also at the crappiest MR images in history. Okay. However, it's the first. Okay. So pioneering something doesn't have to make it perfect. Okay. But he pioneered spatial localization. Okay. Fast forward. What we do now is every one of those lines is an FID. But we play with the gradient in the x to go from here to there. This is an x gradient. To blip from this line to say this line, I have a y gradient. So I play in with the gradients x and y and z. I select a slice, and then I have a 2D space. Then I can traverse this 2D space by playing x and y gradients with a pulse sequence. Yeah. With a Fourier transform, I get it. Okay? And Fourier transform works in 1D, works in 2D, works in 3D. So K-space can be in 1D like NMR. It can be in 2D for imaging. There is also 2D NMR, right? I think. Mm-hmm. And it can be in 3D. So we can actually excite the whole volume and encode in 3D. The thing I want you to take out, and probably you're already aware of this, that MRI does not acquire image space. It's not like your phone or your old camera that you take a picture and you print it on the film. That's image space. MRI, and even NMR, collects the data in the Fourier space. We collect the frequencies. And with the Fourier transform, we construct the images. I have a slide for math, But you know, if you need to see it, I can show it to you. And to give you a quick intuition about this, what do we care about the image? Spatial resolution and field of view. That's the first thing. How big is my field of view for the head or for the knee, right? So how do I play with the field of view in an MRI scanner? I play with the spacing of the sampling. So that's what we call reciprocality. So the big part here, how far I go in k-space, 1 over that is my pixel size. Vice versa, how fine I sample, delta kx, 1 over that is my field of view. Reciprocality of Fourier space, Fourier transform, yeah? Okay. And that's essentially, I'm just gonna skip a lot of the, okay, so this is clearly the size I have for this space. Sorry, I have 2 sets of classes. It is actually these. Okay, so to summarize, the MRI scanner has 3 components. The strong magnetic field, that's what you're looking at here, 3 Tesla. The reason it's much bigger than the 500, although the 500 is 11 Tesla, this is 3 Tesla, is because now I have 7 Tesla that covers the whole body. Versus in their case, 500 is maybe covering this, I don't know how much space, like very small space. So I don't need that big of alignment, okay? The gradients to do spatial localization, and the radio frequency. Okay, so I'm going to show you 3 applications. We're going to switch to the demo, and we'll show you a clinical application. Okay, the first application is anatomical scans. Remember the Simpsons picture, structure and function. And today we'll see structure and function for our volunteer. So this is what we call a T1 weighted image. This is what we call a T2 weighted image. What do you think about the difference between them? Contrast. Yeah. So remember when I showed you the side of my brain that is smaller, it's the white matter here. On top of it, you see this ribbon? This is the cortical surface. This is where the action happens. The reason my fingers are moving now is because my left hand now in my motor cortex is giving the order to my fingers to move. It's coming from here to there. Okay? If I touch or I touch something hot, there is a signal that goes from here to the sensory cortex. So there are two-way connections. It's pressure, heat, and pain sensory things. Yeah. Okay. So you're looking at the same. This is the same scan. This is what we call a sagittal view. So you're looking at the side. This is called the coronal view. So you look at the front, and you're cutting front to back or back to front. And this is you're cutting horizontally.
What happens if someone is moving finger while they are doing MRI?
You'll do this today.
So what would happen to the images?
If you move your head,
Yeah.
it's gonna be.
I'm tapping my fingers, and you're doing MRI, and I'm not tapping. Would you be able to see a change in the image that you?
Not the structural scan.
Mhm.
Not the
But
structural scan.
functional.
We'll go to the functional scan. So initially we need to look at structure. You ran this study yesterday, right?
Yeah, I was into that instrument, but I didn't know what all happened.
You didn't.
I tapped, but I didn't see this.
Oh, you didn't see it. Okay, you'll see it today.
Mhm.
Okay. Okay. So what is this bright stuff around the brain? It's fluid. It's called cerebrospinal fluid. Okay. It is used to maintain pressure, remove waste, and so on and so forth. You can remember the brain is fixed in the skull. You see this black thing? This is actually the skull. Okay. And the brain is trapped inside that skull. So when my heart is pumping, blood is going in. That increases pressure. Something has to give. What gives? The cerebrospinal fluid leaves as blood comes in systole. In diastole, blood is coming out. Something have to compensate. Then CSF goes in. If there's a mismatch, you get a disease called hydrocephalus. And that's very common in babies. You see this ventricle? Can become this whole thing. You see this whole tissue? It becomes so thin. Yeah. It's called hydrocephalus. Okay? So there is an intricate balance between all these things happening in the same time. Okay, what we do is we give this to a supercomputer and we do what we call brain segmentation. And this is printed here at NYU, similar to that. So quick anatomy, it's cortex. The brain has frontal lobes, parietal lobes, temporal lobes, and occipital lobes. Okay, you can look at cingulate as well inside. Okay, you can talk about the brain from its lateral view, from its medial view. Okay, so a lot of people will do it. You can look at it from the top, you can look at it from the bottom. Sometimes they call it ventral view from the top, from the bottom. If you look at the bottom like this is ventral view, this is dorsal view. But remember these two words, lateral, medial. Okay, so that's structure. Okay, check. Function. How do we do function? Scan. Tap finger and stop. Tap finger and stop. What happens? This is the phenomenon. It's a phenomenon that is built on the imaging. Okay? You studied T2 star?
T2 star.
Yeah.
I know, but we didn't cover
You
it
do.
last.
You studied T2.
Yes.
Yeah. Okay. So I'll discuss briefly just because you guys know what T2 is. So I'll just upgrade your knowledge by introducing T2 star just briefly. But what happens when I do this for 20 seconds and then I do this for 20 seconds. I do this for 20 seconds. I do this for 20 seconds. Because it's my right hand, here is my hand now on the left side of the brain. So my left hand now, this is the blue thing, is the motor cortex. This is the hand area. Okay. So this is the hand area that controls my hand. If I'm doing this for like 2 minutes, okay, that area is going to become activated, right? It needs to fire. These axons needs to control my hand. Yeah? An electrical signal has to flow. To allow those axons to continue doing what they're doing, they require blood. Okay, they recruit more blood. More oxygenated blood gush into the area that is activated. Again, we need a reference. I cannot do this, then I will have no reference. What I need is a rest and then move. A rest and move. Then I'm going from here to there, here to there, here to there. What happens is deoxygenated. Usually, if there is activation, there is oxygenated blood gushing in. Oxygenated blood is diamagnetic. Deoxygenated blood is paramagnetic. So with a T2 star is usually you see the effect of T2 star when you do you know what the pulse sequence is. Okay, when you do like a single pulse and a choir. Okay, the longer your readout, the more sensitive you are to T2 star. But you understand spin echoes, right? Okay, so let's say you do a 90 degree and then you get an echo that decays quick. The 180 degree is going to revive that echo. Okay, and then you study T2. T2 star happens usually after the first echo. Okay, because it decays very fast because of T2 star. What the 180 degree pulse, it compensates the T2 star and you're studying T2. Okay, so T2 star is like a fast thing. It's very sensitive to susceptibility changes. And that's from deoxygenated blood to oxygenated blood. The sequence, the commercial name of that sequence in MRI literature is called BOLD. Blood oxygenation level dependent is nothing but a T2 star. A gradient echo sequence. You studied gradient echo? Oh. Which is essentially pulse acquire with some gradients to do imaging. Here is a BOLD image. We acquired this whole brain, 72 slices, in 1 second. So it's very fast. That's what allows us to add the temporal dimension, a time dimension. So it's not 3D data anymore, it's 4D data. Look at this voxel here, we call it voxel, not pixel. And look at this signal here. This is time. Every one of those points is a second, is a volume. I'm just taking that single dot here in the visual cortex in the medial surface. And then the y-axis is percent signal change. So it goes from 2% to minus 6%. So I have like about 8% difference dropping. Why? What happened? What was this patient doing? she wasn't a patient, she was a nurse in Cleveland Clinic. She was breathing normally for 40 seconds and holding her breath for 15. We told her what to do. We gave her instructions on the screen. Breathe, stop. Breathe, stop. You know? Breathe, stop, breathe. What happens when you stop breathing? More CO2 builds up, more deoxygenated blood in your brain. That actually drops the signal. This is the phenomenon we are exposing when we are doing functional MRI, say for language, for motor, for vision, for memory, for speech processing. It's actually using this phenomenon that differences in activated, not activated states, axon firing translates into a blood oxygenation change. That's what we call the neurovascular coupling. Okay, and that's what you're going to see today in real time as Asif is running his section. He's running this one. Okay, here's an example of a study. This is a language study. See gibberish? Your brain already knows. This is gibberish. It already knows that this is language, right? So I ask you to fill in the blank. Why do I do this rest? Because if I cannot put a blank screen, because otherwise I'm going to be stimulating your visual cortex. I'm not interested in your visual cortex for this part of the study. I'm interested only in language. So I maintain the same length of sentence, so your visual cortex is getting the same stimulation, but your brain knows, oh, I cannot fill in the blank here, I can fill in like ocean here or something, okay? Then that actually only activates the areas that associate with language, okay? And it looks, I think, like this, see, these areas, and not the whole brain is involved in language, usually it's on the left side. Here's another visual stimulus. So this stimulates the visual cortex, and again, the medial side of the brain, the back part of it, this thing is the primary visual cortex.
Sorry, I'm grabbing the
Okay, so we talked about structure, we talked about function. How does my motor cortex reach to my hands? Structural functional relationship, the highways, white matter pathways, they look actually like this. Okay, so that's this thing. Okay, it's not like just a single like continuous that. These are all different tracts, and this is corona radiata. This is superior longitudinal. This is optic radiation. Okay. So there are different tracks in here. You cannot appreciate what are the different tracks from here by looking at this. You think, oh, white matter, they're all white matter. No, actually they are separated functionally and structurally separate. So if I give you a cadaver head, fixed, formalin fixed, and say, can you please expose optic radiation for me? And we teach you all the techniques. It takes you 50 days to go from a full head into this beautiful view. And of course, lots of skill and patience. Or you can put it in an MRI scanner. You study diffusion imaging, diffusion. Okay. We do a diffusion sequence. Okay, we encode diffusion in 3 dimensions. We can do this in about 3-4 minutes. Okay, so we can do virtual dissection in a few minutes. Okay, clinical application. Our colleague here, she shows up to Cleveland Clinic. The surgeon calls me, your colleague has brain tumor. So we scanned her at Cleveland, we did the brain segmentation, here's her tumor, structure, right? We're interested in structure. So now you're seeing an application of this multimodal structure, function, and really, motor cortex, sensory cortex, some language areas. This is from the lateral view, this is from the top view. These are the highways. See this bundle here? This is the motor bundle. It connects to her motor cortex, to the spinal cord. So not only the surgeon has to protect the cortical areas, he has to protect the highways. Because what's good for those cortical areas if you cut the cord, yeah? Your computer is working, but you cut the cord, the hand. There is no way back, it's paralysis. Okay? In the contralateral side. So this is the left side. So we were worried about her right foot because the tumor was in the top. See the top? This is her actually foot area here. So the surgeon was very worried about her foot. He actually warned her that she might actually end up on a wheelchair after the surgery. Well, she was in Dubai Mall 2 weeks later. Here's the arcuate fasciculus. It looks like an arc, so we call it the iris in green. And this is the superior longifaciculus. It's actually a language tract. If you chop this tract, you can't talk. Okay? You cannot talk, or you cannot, even if you can talk, sometimes you cannot say understood sentences, depending on the location of the insult. Insults here, you will have problems with initiating speech. Problems here, you will have you will be able to produce, but you produce what they call garbage language. Okay, here's a functional MRI. I'm taking a sagittal cut. The red stains is the result of the language functional MRI, and the yellow stains is the terminations of the SLF, the superior fasciculus. So we overlaid structure, function, and structural functional connection. Okay, that is an application of what you just of an MRI, just in real time. It's a person that can happen to anyone else. Any one of us can end up with a brain tumor. Okay, so this is a quick overview of what we do. MRI uses non-ionizing radiation, highly versatile. I have a picture of my head, a picture of my heart, my knees, and my toes. It's barely the picture of my toes. It gives superb soft tissue contrast. It can image structure, function, and the connections between them. However, it's very expensive. You know, a couple $1 million it cost, yet alone to be in an educational institution like this, it's unheard of. This is a cash-making machine. In Cleveland Clinic, they run it 24/7, 7 days a week. They take maybe 2 days break in the year, and that's it. And they have 4 scanners. And they generate millions and millions of dollars daily from the MRI scanner. Here we are sitting in a relaxed setting and just enjoying, a boring lecture by a troublemaker. And potential complication. It's a very big magnet. This magnet can actually pull a truck. You know, junkyards, they have 1 Tesla magnet to pull a truck from one side to another. So if this chair gets stuck there, well, it will fly like a missile. We call it the missile effect. You know, in our environmental health and safety risk assessment. What are the risks associated with MRI? Missile effects. It has a name actually, because things fly like a missile inside. That's why I will not trust a huge group inside the magnet room with a subject, because I don't know. I have to screen each one of them. I have to have them change like you. So it's complicated. Okay, we can, but we have to screen every single one of them just to make sure that you are safe when you are inside. Yeah, and prizes and all that. So it requires training. Okay, and that was one of the challenges to come to campus and have a big magnet like this. Our cleaners are trained. Our garbage cans are MR safe. There's no metals in them. Our fire extinguishers are MR conditional. I don't have the red fire extinguishers around campus. They're all out of this, because these things will not fly. The red ones will fly inside. Yeah. So it's a very tight space. Anybody who's sitting here has to be escorted by an MR safety officer or an MR trained person. Okay. So now, I think. Now your turn. 80. Okay. The cool thing is, we'll be able to see. Hades screen.
Buy glasses too.
You need to let go of your glasses. Yes. We have glasses. If you cannot see, we have glasses. Questions? Oh.
I do have a question.
Yeah.
If that thing attracting metal is a problem, like in MRI, like in NMR machines and in our ERB we have it's shielded. So
The shielding means that the fringe field doesn't spill too far.
yes.
And this is a shielded machine. Okay. So inside, it's 3 Tesla.
Yes.
So it's 30,000 gauss. By this door, it's 5 gauss.
Okay.
So in only 3 meters, you go from 5 gauss to 30,000 gauss. Okay, and that's what the shielding does. In the old days, before they invented the shielded magnets, the 5 gauss line is where you're sitting. So the room has to be a lot bigger. Okay? So yeah, shielding reduces the fringe field. But if you cross the 35 Gauss line, things will start flying out of your head. You cannot carry. It will be a sudden, and there are videos on YouTube to show, like flying a fire extinguisher, a wrench, this, that. Yeah. Okay, so Haiti is making Asif comfortable. He will see what you see on that screen. Okay, so whatever you see on that screen, he's going to see inside. And the gradients, unlike an NMR machine, which is very silent. Is it silent? Is it
It's very silent.
very silent? The NMR machine. You're familiar with MRI? Okay, have you been here? You've been here?
I've been in my freshman year. I was part of a study conducted, and I was a subject twice.
So be prepared for some knocking. Yeah. The gradient.
Knocking is an understatement.
I agree. I mean, I don't want to freak them out. Oh.
You can hear the canvas, right? Inside?
Yeah, we have what's it? So it's like a probe. She's pushing that bed in the center of the magnet. The gradient is built in the walls of the magnet in the bore. The coil, it looks like a stormtrooper helmet. It has a mirror attached on top, so he can see to the back. See, she's pulling him up. You can see his eyes. We have an eye tracker inside the magnet, so if he sleeps, we wake him up. Yeah, he's speaking out. I'm just kidding. So we use MATLAB to control the stimulus presentation. In this case, all what we're gonna do is like move and stop. So Haiti, we wanna do a quick. Actually, you can skip the anatomical scan, just localizer and then and the finger tap. You agree? Okay. So what Haiti is doing is now she's going to run a scout scan. She just wants to make sure that his head is in the center of the magnet. So we're going to get a sagittal, axial, and coronal cuts. It's usually quick, like 10-15 seconds. We're going to get some quick localizer. Okay, so now, see this is the tongue, this is the cerebellum, this is the nose, and she's taking slices that way, yeah? We don't need the motion like that. This, yeah, because he wants to see his activation. So if we haven't loaded the neural 3D, it will be great. Yeah.
I have a question. This MRI is just taking one scan per round, right?
Per round? What do you mean by round? And remember, we have multiple types of scans. We talk anatomical, functional. What type of scans we talk about?
Functional is with time scale, just static. I think anatomical.
Anatomical, yes.
Because in NMRs we have like 5 scans, 15 scans experiments, like 1,000 scan experiment to enhance resolution.
To enhance signal to noise.
Yes.
Okay, that's averaging.
Yes.
Okay. So yes, we do averaging. I think the anatomical scan we're doing 2 averages. But yeah, we do averaging all the time. The both scans, the functional scans, we do just a single average, so we don't waste time. There is always a balance between resolution and signal to noise.
Yes.
Okay, so now he's doing the functional task. See, he has now stop and tap fingers, and then we were not going to tell you which fingers he's tapping. Can you load the? This is the. I don't need to say anything to him. Okay. So now these are cuts through his brain into. You're looking at the top slice is here, the bottom slice is there. Here's his eyes. Yeah. And you can see functional activation localized mostly toward the top, not exactly the top of the brain, but toward the higher slices of the brain. This is the right side, so there's a right here. This is the left side. Okay. See this location? This is where his hand mount is. So his hand area. So without us knowing which hand he's moving, it's on the left side. And we know the left side is controlled by the right motor cortex, so we know he's moving his right hand. Yeah. Okay, he's good to go. And now we will, okay, yeah, you can stop. I think we will now, yeah, we will now look at, yeah.
The 2 taxes. Anatomical is just on the basic pad and then the Euro 3D scan.
So we wait for him to come because I know he was super excited to see his brain. So we pre-collected high resolution scans for him because the high resolution scans takes about 6-7 minutes. So rather than us waiting for 6-7 minutes, we collected the quick localizer so you get the point, and he wants to see. So he's curious. I want him out. See, this is his head. Yeah. If there is a girl with lots of hair, then you're like, why you look like that? He's like, yeah, but you know, we guys, we just pretty much look like ourselves. Okay. So yeah, it's acquiring, you see, any tissue that has hydrogen shows. Okay? Because different tissues have different T1s and T2s. Okay? And then you can actually put it in your slides, like when you put it in your profile at NYU. This is how. Okay, but here's the brain. Yeah.
Is there any disease?
If there is, we cannot tell you. We will send you anatomicals to a certified radiologist, and they will contact you directly. They will not pass through us. Okay. If you sign the release, you need to sign. You sign the release.
Mm-hmm.
Okay, so you get a free radiologist there. Okay. Here are the carotid vessels. These are the vessels that feeds the brain. You see here the spinal cord. Yeah. Okay. You see the cerebellum here. Okay. You see now we are looking at the lateral view here. Okay. So now where is the motor area? See? So which side of the brain is this? Let's look at him facing us. So Asif now is facing us. So this is his right side. And this is his left side. And see here, This is actually his motor area and sensory area, because it looks like he was touching his fingers. So not only he was moving it, but he was touching it. So we have activation both in the sensory and the motor. Okay. He's done a different task the other day as well. We just had him do it for fun. We showed him a task that can you show the motion localized task? You see the activity here and activity here. This is for a different task that we showed. We just wanted to look. I want to speak like Dr. Seuss now. Did you ever have the feeling that there is? You know what I'm talking about here. There is a basket in your basket. I read it to my son every day, so I memorize the whole thing. But did you ever have the feeling that there is something crawling on the floor, and then he's like, oh, okay, you just see it? Why? Because there is actually an area in your brain called area MT that is sensitive to motion, and that's how we analyze it. We show moving dots, and then for like 15-20 seconds, and then stop. Okay, so the visual input is the same. So I'm not interested in your primary visual cortex. I'm interested in the motion areas. And it turns out that the motion areas, they call area MT, is actually located in the middle temporal lobe. So let's talk some anatomy. We said that this is the temporal lobe. It has a superior, middle, and inferior temporal gyre. Yeah? Superior temporal gyrus, STG, middle temporal gyrus, MTG, IFG, inferior frontal gyrus. Area MT is in the middle temple. Okay, and that's where your area MT is. Here, it's bilateral, so it's actually here. You still get some activity in the visual area, but also we get activity in the middle temple. Okay, so let's talk brain anatomy. See? Now I'm cutting from back to the front. See the eyes? Okay, we cut. Let's focus on this view now. Okay, so I'm going to go all the way to the bottom. Okay. So I'm cutting from the neck. See the spinal cord here? Coming up. See the tongue? Coming up, coming up, coming up. See the cerebellum here? Okay. Okay. Now let's talk about the visual system quickly. Let's find the eyes. Here are the eyes. Okay. He was moving his eyes. You see what motion does? When you say what does motion do? It's actually it's this ringing. See this ringing thing? As if you're like taking a picture with your camera and your hand is shaking. Okay? But look at this. You see here there is it's very hard to see because he was moving, but there is a nerve, this nerve, coming to the eye, and then that nerve see here's the nerve here. See it? See this? It's the optic nerve. See this? It crosses. Okay? And that's what we call the optic chiasm. So the fibers on the lateral side of the optic nerve stays on the same side of the brain. The fibers on the nasal side of the optic nerve crosses to the other side. Okay? On the optic chiasm. This is where they cross it. And whatever I see on my right crosses to the left brain. Whatever I see on the left crosses to the right brain, and then flipped upside down. There's two flips, this and that. Okay, and that's happening because of this. And this information travels from the eye. Remember that retina for the engineers is a transducer. It transduces photons to electrical signal. Right? And that electrical signal is transferred through these axons, through the optic nerves, optic chiasm, and let's follow the optic chiasm. Let's follow it on a different, let's follow it, see. See the optic chiasm enters the brain. This is now called the optic tract. See the optic tract here? The optic tract stops about here. What we call it synapses. That means it terminates in a hub. We call it the LGN, the lateral geniculate nucleus of the thalamus. Then that LGN transmits the information back to the visual cortex, which is the fibers. Let's see, let's find the visual pathway fibers. It's these. So this is the optic radiation fibers coming here, and you see this is visual activation. This is like the visual activation task. So you see that optic radiation is terminating in the visual cortex. Okay, so I have 5 more minutes, and then I'll let you go. So what do we do with this information? Let's see. If you're grossed out by pictures of brain surgeries, open skulls, and brain tumors being removed, you can look away. I'm still gonna play it, okay? But I'm warning you, it's not gross for me, but it could be gross for some people. Okay, so this is an example.
Let's think about the brain surgery. Whenever we have a patient who has been diagnosed with a tumor or brain lesion, very close proximity to an endocrine or very functional brain area. This enables us to perform microsurgical resection without compromising any functional disability in the patient afterwards. Even more, it requires a deep understanding of the language generation in humans. Human being has several language centers, which are responsible for word recognition, sentence completion, rhyming, and even auditory and visual inputs to generate the comprehensive skills of a language. So all the different teams come together, like neuroanesthesia and electrophysiology team, which are integral parts of that type of procedure. I'm very proud to have a very strong collaboration with the New York University Abu Dhabi, where they help us to process the functional MRI images we generate here at the Cleveland Clinic Abu Dhabi.
We deployed 3 advanced imaging modalities. The first modality was advanced structural analysis. You know, the 3 modalities. Structural, functional, and
in its relationship with the neighboring brain areas. The second modality that we added was actually functional MRI, where we asked the patient to conduct specific tasks inside the MRI scanner. For example, complete a sentence or generate
language tasks,
or generate a verb, and so on and so forth. And those areas were lit up in the MRI scanner to help the surgeon identify the so-called eloquent cortex. And to show the connectivity between these cortices areas or functional areas
So the white matter
to the rest of the brain,
for this patient.
we deployed the third advanced modality, which is called diffusion tractography, which maps the white matter fiber bundles in the brain, or if you will, it's just the highways that connects the different functional areas in the brain.
So we do a lot of pre-surgical testing with those patients, as well as
It's an actual patient.
through the OR the
This is
day
not a
before,
demonstration.
just to make the patient familiar with the surrounding, with the voices and the faces of each caregiver who will be part of the team.
Neurologist,
During the day of
anesthesiologist,
surgery, we
neurosurgeon,
follow the concept of sleep,
It's a big
awake,
team.
sleep.
about
So
15
for the
people.
beginning, the patient will sleep, as this is the potentially painful part of the procedure when you expose the brain and do the craniotomy with the bone flap removal. But the moment the brain is exposed, we have to start mapping the surface of the brain to identify the function. We basically bring together the information derived from the functional MRI imaging and from the pre-surgical assessment onto the patient's brain in that situation. Basically, every single instrument I can use, I can navigate with the help of the most modern equipment we have that at any given time during the case, I know exactly in which area of the brain I am.
This is during the surgery.
Patient is
So
awake,
you can look at the fiber during the surgery.
surface,
She's awake,
motor
she's
function,
talking, he's
sensory
removing his
function,
tumor,
and
her
of
tumor.
course the complex assessment of language and speech generation during.
Okay, see this?
Mhm.
Tumor boundary. This way. Yeah.
At any given time, we have to make a good balance between neuro-oncology.
See this small
needs,
tweezer?
what
It's a
basically
very
means
fine
that we
tip.
have to remove
Use a
as much
microscope
tumor as possible
to magnify.
within the healthy surrounding brain. On the other hand, we want to preserve function because quality of life is essential, especially when we talk about language preservation. In this particular case, we could even go much further. Depending on the intellectual abilities, we can assess higher cognitive functions.
This is our colleague, we gave her a paper to read during the surgery. He was interrogating her on the hypothesis as he was taking her to
Wow.
So with the strong collaboration we have between the New York University Abu Dhabi and the Cleveland Clinic Abu Dhabi, it enables us to perform surgeries which have never been done in the UAE and beyond. It gives us the opportunity to have patients treated here at home with the full assessment and the outcome of what is needed. Especially now that we translate the functional MRI data in Arabic language is something which has never been validated across the world, as most of the research protocols for language testing were assessed in English. I'm proud to say that we can even go further and have much more innovative ideas to include in these protocols, such as artificial intelligence or robotic applications for even higher precision in pre-surgical mapping and intraoperative verification of all these informations.
Okay, cool. So, good luck. Any other questions?
I think that was wonderful. Thank you.
You're welcome. I haven't even talked about spectroscopy that we do here. But yeah. We do some in vivo spectroscopy, but we don't do it on a routine basis to look at metabolites in the brain. And some tumors have elevated choline. It's a marker for malignancy in tumors, so they do it routinely. Okay, cool. Anything else? Okay, you guys have a good evening.
Very much.
You're welcome.
It was amazing experience for me.